Hello, friend. Come closer. Let the world outside fade for a moment. Tonight we are going somewhere quiet, somewhere dark, somewhere most people never think to look. We're going to the universe before there were stars, before there was light to see by, before anything shone. Close your eyes if you'd like. This story doesn't need them. Imagine standing in a field at night far from any city. The stars fill the sky like scattered diamonds on black velvet, thousands of them. Maybe millions if the night is clear enough. But here's something strange to consider. There was a time when none of this existed. Not one star, not one galaxy, not a single point of light anywhere in the entire universe. Just darkness. Pure, endless, absolute darkness. The kind of dark that makes the deepest ocean trench seem bright by comparison. Before we drift into that ancient night together, if you find comfort in these quiet journeys through time and space, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell, not for noise, but so the next quiet night can find you again when you need it most. Now, let's drift. Tonight, we'll float backward through time, past everything, familiar, past stars and planets, past light itself into the silent ages when the universe was young and dark and waiting. We call this period the Dark Ages of the Cosmos, and it lasted far longer than all of human civilization, longer than the dinosaurs walked the earth, longer than our planet has existed. From about 380,000 years after the Big Bang until roughly 150 million years later, the universe sat in darkness, holding its breath, preparing for the light that would eventually come. You don't need to understand everything. Just rest and let curiosity do the listening. Some numbers are too large to feel. 380,000 years, 150 million years. Our minds weren't built to hold spans of time like that, but perhaps we can understand them differently. If the entire history of the universe were a single year, with the Big Bang happening at midnight on January 1st, this dark period would begin about 2 hours later, at 2 in the morning, and it would last for nearly 3 weeks. 3 weeks of pure darkness in the cosmic calendar. No dawn, no twilight. Just night stretching on and on. Scientists often talk about the beginning, about the Big Bang, as if it were simple, as if we could just say, it happened and move on. But the truth is stranger and softer than most people realize. In the very first moments after the universe began, there was no darkness because there was no space for darkness to fill. Everything that would become everything existed in a space smaller than an atom. All the matter that would eventually form every star, every planet, every grain of sand on every beach existed in a point so small we have no words that properly describe it. And it was hot. Not hot like a fire or hot like the surface of the sun. Hot in a way that would make the sun seem frozen by comparison. In the first trillionth of a trillionth of a trillionth of a second, the temperature was so extreme that matter as we know it couldn't exist. There were no atoms, no protons or neutrons. Not even the quarks that make up protons and neutrons. Just pure energy seething and expanding at speeds our minds cannot truly grasp. Light and matter were the same thing then, indistinguishable mixed together, in what physicists sometimes call a quark-gluon plasma. It sounds technical, but imagine it instead as a sort of cosmic soup, thick with possibility, where nothing had settled into its final form yet. Then in the first microsecond, something remarkable happened. The universe cooled just enough for quarks to stick together. 3 quarks formed a proton. 3 different quarks formed a neutron. These are the building blocks of every atom that would ever exist, and they came into being in less time than it takes light to cross a single grain of salt. Within the first 3 minutes, something else occurred. These protons and neutrons began to find each other in the chaos and stick together. Nuclear fusion, the same process that powers the sun, happened everywhere at once throughout the entire universe. Protons fused together to form the nuclei of hydrogen atoms. Some hydrogen nuclei captured additional neutrons to become deuterium-heavy hydrogen. And some of these merged further to create helium, the second lightest element. In those 3 minutes, the universe made almost all the hydrogen and helium that exists today. About 3/4 hydrogen, 1/4 helium, with just tiny traces of lithium. That's all. 3 elements. The periodic table had only 3 entries, and it would stay that way for a very long time. Research shows that these proportions 3:1, hydrogen to helium, appear everywhere we look in the universe. It's one of the strongest pieces of evidence we have that the Big Bang actually happened. The math predicted it before we measured it, and when we finally could measure it, the numbers matched. That quiet agreement between mathematics and reality is one of the most beautiful confirmations in all of science. But here's what matters for our story tonight. Even though atoms were beginning to form, even though the universe now had hydrogen and helium, it still wasn't transparent. It was more like a thick fog. Photons, particles of light, couldn't travel freely. Every time a photon tried to move, it would almost immediately crash into a free electron. The electrons were everywhere, zipping around, not yet bound to atomic nuclei, and they scattered light in every direction. Imagine trying to see through a cloud made of mirrors. That was the universe then, full of light, but unable to see anything, because the light itself was trapped, bouncing endlessly from particle to particle. This state, this fog of scattered light and free electrons, had a name. Physicists call it a plasma. The universe was one vast plasma stretching in all directions, opaque and glowing, and unable to let light pass through. This isn't darkness yet. This is the opposite in a way. This is light imprisoned, and it would remain this way for nearly 400,000 years. The same amount of time it took for modern humans to spread across the earth, from the first stone tools to the first cities. The universe stayed in this state, cooling slowly, waiting for the moment when it could finally become transparent. That moment came not with a flash, but with a gradual settling. As the universe expanded, it cooled. And at a certain temperature around 3,000 degrees, Kelvin, still hotter than any furnace we can build. But cool compared to the billions of degrees it had been, something shifted. Electrons which had been flying free began to slow down enough to be captured by the nuclei of hydrogen and helium atoms. Scientists call this event recombination, which is a slightly misleading name because the electrons and nuclei were combining for the first time, not recombining. But names aside, this was one of the most important transitions in cosmic history. When electrons joined with nuclei to form complete atoms, suddenly there were far fewer free electrons bouncing around. And photons, which had been trapped for hundreds of thousands of years, were suddenly free to travel. The fog lifted. The universe became transparent. Light could finally journey across space without being scattered. This moment, this transition from opaque to transparent, happened everywhere in the universe at roughly the same time. Not instantaneously, because the universe is so vast that the same time has a different meaning on cosmic scales, but within a relatively brief window of a few tens of thousands of years. The light that was released at that moment is still traveling. We can still see it, in fact. We call it the cosmic microwave background, the CMB. It fills the entire sky, coming from every direction at once. It's the oldest light we can observe, a sort of baby picture of the universe taken when it was only 380,000 years old. When telescopes measure this light, they see the universe as it was then smooth and nearly uniform, with only tiny ripples of density that would eventually become the seeds of galaxies. The temperature of this light when it was released was about 3,000 Kelvin. But because the universe has been expanding ever since, the wavelength of this light has been stretched. What was once visible light glowing orange-red has been stretched into microwaves. Today, if we measure the cosmic microwave background, we find it has a temperature of just 2.7 degrees above absolute zero. The echo of creation cooled by 14 billion years of expansion. But here's the strange part. Even though the universe became transparent, even though light could finally travel freely, it was about to become dark, because there were no sources of light. No stars had formed yet, no galaxies, no quasars. Nothing was burning, nothing was shining. The universe was filled with hydrogen and helium. Gas spread almost uniformly through space, with only the faintest variations in density. It was transparent, yes, but empty, like a perfectly clear night with no moon and no stars. You could see forever if there were eyes to see, but there would be nothing to see. This is when the Dark Ages began, not because the universe was opaque as it had been before, but because it was empty of light sources. The cosmic microwave background was fading, red shifting into longer and longer wavelengths, becoming dimmer and dimmer. And there was nothing else, no campfires in the cosmic night, just gas cooling and drifting in the dark. Scientists estimate this darkness lasted for tens of millions of years, maybe 100 million, maybe more. The exact timing is still uncertain because this era is difficult to observe. We can't see it directly because there was nothing to emit light for us to see. We can only infer what it was like from the conditions before and after from computer simulations and mathematical models. But those models paint a consistent picture. A universe filled with hydrogen and helium, cooling slowly from 3,000 degrees down toward the temperature of deep space with no light except the fading afterglow of the Big Bang itself. Imagine floating in that universe if such a thing were possible. You would feel nothing, see nothing. No up, no down, no heat, no cold you could distinguish. Just an endless sameness extending in every direction. The gas around you would be so thin that even calling it gas seems generous. Thinner than the best vacuum we can create in laboratories on Earth. A few atoms per cubic meter, perhaps, maybe fewer. And yet those atoms were all there was, hydrogen mostly, helium, whispers of lithium, the raw materials for everything that would come later, just waiting in the dark. But even in that emptiness, even in that darkness, something was happening. The gas wasn't perfectly uniform. The cosmic microwave background shows us that. There were regions very slightly denser than others. Tiny fluctuations in density leftovers from quantum fluctuations in the earliest moments of the Big Bang, amplified by the expansion of space itself. In most places, the gas was spread evenly, but in some places, there was just a little bit more, and gravity, patient and inevitable, began to pull on those denser regions. At first, nothing seemed to change. The differences were so small. A region might be 1 part in 100,000 denser than its surroundings. But gravity doesn't care about dramatic differences. It only cares about mass. And wherever there was a little more mass, gravity pulled a little harder. Slowly, almost imperceptibly, gas began to drift toward these slightly denser regions. And as more gas accumulated, the gravitational pull grew stronger, drawing in even more gas. It was a feedback loop, gentle at first, but accelerating over time. Have you ever watched water begin to swirl down a drain? At first, the motion is barely visible, but once it starts, it builds on itself faster and faster. The Dark Ages were like that. A slow gathering, a patient assembly of matter in the darkness, guided by gravity's invisible hand. Regions that had been only slightly denser became noticeably denser, and the densest regions began to pull away from their surroundings, forming distinct structures. Scientists call these structures dark matter halos, though calling them halos makes them sound more solid than they were. They were more like gentle hills in the density of space places where matter preferred to be. And into these hills, hydrogen and helium gas began to flow, collecting compressing warming from the friction of atoms bumping into each other. It was still dark, still silent, but the universe was no longer uniform. It was beginning to have shape. These weren't the only things happening in the dark. The universe was also expanding, carrying everything farther apart. As space expanded, it stretched the gas, thinning it out. This expansion fought against gravity's pull to bring things together. In some regions, expansion won, and the gas stayed thin and diffuse. In other regions where the initial density was just high enough, gravity won, and the gas kept falling inward despite the expansion. It's a kind of cosmic tug-of-war one that's still happening today. But back then in the Dark Ages, the outcome wasn't yet clear. The universe was still young enough that most of its matter hadn't decided which side it was on. Would it stay spread out drifting in the dark forever? Or would it gather together, pulled by gravity into dense knots that could someday become something more? We know now how this story ends, or at least we know the next chapter. The dense regions won at least in some places. Gas collected, compressed, grew warmer and warmer, until it reached temperatures high enough to ignite. Stars formed. Light returned to the universe. But that's not where we are yet. Right now, we're still in the dark, watching the slow gathering, feeling the patient pull of gravity in a universe that hasn't yet learned to shine. The Dark Ages were not an accident or a mistake. They were a necessary pause, a moment for the universe to catch its breath after the violence of its birth, a time for matter to spread out, cool down, and begin the slow work of organizing itself. Without this period of darkness and cooling the structures we see today, the galaxies and stars and planets could never have formed. The universe needed to be dark before it could be bright. It needed to be empty before it could be full. And perhaps there's something quietly beautiful in that, in knowing that even the universe needed time, that even creation itself had to wait, had to sit in darkness, gathering strength for what would come next. The darkness wasn't empty after all. It was full of potential. Every atom of hydrogen, every atom of helium was waiting. The stage was being set. The pieces were moving into place. And somewhere in that dark, in those first dense regions where gas was gathering, the first stars were beginning to dream themselves into existence. But they're not born yet. For now, we're still floating in the quiet, still waiting in the dark, still listening to the universe breathe in silence, preparing for the light that will eventually come. And in this moment, in this long pause between the birth of matter and the birth of stars, there's a kind of peace. The peace of a universe that doesn't yet know what it will become. The peace of darkness that doesn't yet know it's dark because there's nothing to compare it to. We'll leave it here for now, in this quiet space between creation and illumination. The universe transparent but dark, empty, but not lifeless, waiting patiently for gravity to finish its work. And as we drift forward through time toward the moment when the first light will finally break through the darkness, we might notice something. That even in the deepest night, even in the longest silence, there are processes at work, invisible threads pulling, atoms gathering, density increasing, the slow, patient assembly of everything that will matter. The darkness we've been floating in wasn't always dark. Before the Dark Ages, before the silence, before the waiting, there was fire. Not the kind of fire you can warm your hands by. Not even the kind that burns in the heart of the sun. Something far more primal, far more violent, far more complete. Let's go back further, back to the very beginning, back to the moment when time itself began. Scientists call it the Big Bang, though that name makes it sound like an explosion in space, like fireworks on the 4th of July. But it wasn't an explosion in space. It was an explosion of space. Space itself was born in that moment, along with time, along with energy, along with everything that would ever exist. Before the Big Bang, there was no before, no clock ticking, no emptiness waiting to be filled. The question, what came before, doesn't quite make sense, like asking what's north of the North Pole. Time began here at this point in this instant that lasted no time at all. In the first moment, the observable universe, everything we can see in any direction with our most powerful telescopes, was compressed into a region smaller than a single atom. Some physicists suggest it might have been even smaller than a proton, smaller than a quark, a point with no dimension called a singularity. Though even that word is just mathematics trying to describe something that breaks every rule we know. And the temperature at that singularity was infinite. Or rather, the concept of temperature didn't exist yet, because temperature requires particles to vibrate and collide, and there were no particles yet. Just pure energy condensed beyond imagination. Then, in the tiniest fraction of a second, something shifted. The universe began to expand, not into anything, There was no container, no void waiting to be filled. The expansion was the creation of space itself, growing from nothing, stretching in all directions at once. In the first trillionth of a trillionth of a trillionth of a second, the universe doubled in size, then doubled again, and again, and again, exponentially faster than light itself, because the speed of light is a limit on how fast things can move through space, not a limit on how fast space itself can expand. Scientists call this brief moment inflation. It lasted perhaps 10 to the negative 32 seconds. That's a decimal point followed by 31 zeros and then a 1. A time so short that our brains have no intuition for it. But in that incomprehensibly brief instant, the universe grew from smaller than an atom to roughly the size of a marble or perhaps a beach ball, depending on which models you trust. And embedded in that expansion were tiny quantum fluctuations, random variations in energy density stretched across vast distances. These fluctuations would later become the seeds of galaxies, of clusters, of all the structure we see in the universe today. But that comes much later. For now, they're just ripples in the fabric of space-time, invisible and waiting. When inflation ended, the universe was still unimaginably hot and dense, but it was no longer infinite. It had cooled to around 10 to the 27th degrees Kelvin. That number is so large it loses meaning, but try to imagine it this way. The core of the sun is about 15 million degrees. The surface of a nuclear explosion is perhaps 100 million degrees. The temperature of the universe, a fraction of a second after the Big Bang, was a trillion times hotter than that. At this temperature matter, as we understand, it couldn't exist. Even the fundamental particles, the quarks and electrons that make up atoms, couldn't exist in their normal forms. Instead, there was a sort of primordial soup, a quark-gluon plasma, where quarks and gluons, the particles that normally bind together to form protons and neutrons, floated freely unbound, mingling with photons and other exotic particles we rarely see today. This state didn't last long. The universe was expanding, and as it expanded, it cooled. Within the first microsecond, 1/1,000,000th of a second after the Big Bang began, the temperature dropped low enough for quarks to stick together. 3 quarks combined to form a proton, the nucleus of a hydrogen atom. 3 different quarks combined to form a neutron. This process, called hadronization, happened everywhere at once. The quark-gluon plasma condensed into a hadron soup, a sea of protons and neutrons, and their antimatter counterparts all crashing into each other in the chaos. But matter and antimatter don't coexist peacefully. When a particle meets its antiparticle, both annihilate in a burst of pure energy. For every billion protons, there were roughly a billion antiprotons. They collided, they annihilated, and they released photons, light energy flooding back into the universe. But there was an asymmetry, a tiny imbalance. For every billion matter-antimatter pairs that destroyed each other, there was one extra matter particle left over. 1 proton out of a billion survived. 1 neutron out of a billion remained. This tiny imbalance is why anything exists at all. If matter and antimatter had been perfectly balanced, they would have annihilated completely, leaving nothing but light. No atoms, no stars, no us. The universe would be nothing but a fading glow of photons expanding forever into emptiness. Scientists still don't fully understand why this asymmetry existed. It's one of the deepest mysteries in physics, but we can observe the consequences. Every atom in your body, every star in the sky, every planet, every grain of dust exists because of that 1 in a billion imbalance in the first microsecond of cosmic history. You are made from the leftovers of an ancient annihilation. The survivors of a battle between matter and its mirror image fought when the universe was smaller than a city and hotter than we can comprehend. As the first second ticked by, the universe continued to cool. By the time it was 1 second old, the temperature had dropped to about 10 billion degrees Kelvin, still unimaginably hot, but cool enough for something important to happen. Neutrons, which are slightly heavier than protons, began to decay. A free neutron left alone will naturally transform into a proton, releasing an electron and a neutrino in the process. This decay takes about 10 minutes on average, but in the chaos of the early universe with particles colliding constantly, some neutrons decayed quickly, while others were captured by protons before they had a chance to fall apart. This is where the story of the first atoms truly begins. In the first 3 minutes after the Big Bang, the universe was a nuclear fusion reactor. Not here and there, not in pockets or regions, but everywhere at once. Every cubic centimeter of space was hot enough and dense enough for nuclear fusion to occur. Protons slammed together with enough energy to overcome their electromagnetic repulsion and stick. A single proton is the nucleus of hydrogen, the simplest atom. But when two protons fused together, along with one or two neutrons, they formed deuterium-heavy hydrogen. And deuterium was unstable in this environment. It quickly fused with another proton or deuterium nucleus to form helium-3 or helium-4, stable isotopes of helium, the second lightest element. This process is called Big Bang nucleosynthesis, and it's one of the most precisely understood events in all of cosmology. The mathematics behind it was worked out in the 1940s and 50s by physicists like George Gamow, Ralph Alpher, and Robert Herman, long before we had the technology to test their predictions. They calculated that in the first 3 minutes, the universe should have converted about 25% of its mass into helium, with the remaining 75% staying as hydrogen. Tiny amounts of deuterium-helium-3 and lithium-7 should also have formed, but in much smaller quantities. Decades later, when astronomers finally had the tools to measure the chemical composition of the oldest stars and gas clouds, they found exactly what the theory predicted. Roughly 75% hydrogen, 25% helium, with trace amounts of deuterium and lithium. This match between prediction and observation is one of the strongest pieces of evidence we have for the Big Bang. The universe tells us its own history if we know how to listen. And the ratio of hydrogen to helium, 3-to-1, is part of that story, written in the very atoms that make up everything we see. After those first 3 minutes, fusion stopped. The universe had expanded and cooled too much for protons and neutrons to collide with enough energy to fuse. The temperature dropped below 1 billion degrees, and nuclear reactions simply couldn't happen anymore. The composition of the universe was set. 3 parts hydrogen, 1 part helium, almost nothing else. It would stay that way for hundreds of thousands of years, but even though fusion had stopped, the universe was still far too hot for atoms to form. Protons and helium nuclei floated freely in a sea of electrons, and more importantly, in a sea of photons. Light was everywhere, packed so densely that it dominated the energy of the universe. For every proton or neutron, there were roughly 1 billion photons. The universe was radiation-dominated, meaning that most of its energy came not from matter, but from light itself. And this light couldn't travel. Every photon that tried to move forward almost immediately collided with a free electron. Electrons are very good at scattering light. They absorb a photon, jostle around, and emit another photon in a random direction. This process, called Thomson scattering, happened constantly everywhere. The result was that light couldn't escape. It was trapped, bouncing from electron to electron, unable to stream freely across space. The universe was opaque. If you could somehow exist in that time, you wouldn't see anything. Not because there was no light, but because the light was trapped in an endless maze of scattering. Imagine standing inside a cloud. Not a thin cloud, but a thick fog so dense you can't see your hand in front of your face. The light is there all around you, but it bounces off the water droplets so many times that it never travels in a straight line long enough to form an image. The early universe was like that, but infinitely more so. A fog made not of water, but of free electrons so thick that light could only travel a tiny distance before scattering again. This state is what physicists call a plasma. Not the plasma in your blood, but a state of matter where electrons have been stripped away from their nuclei by high temperatures, leaving a soup of charged particles and photons all interacting with each other. The sun is made of plasma. Lightning creates a brief flash of plasma in the air, But the early universe was plasma through and through, from one edge to the other, if edges even existed. And this plasma wasn't uniform. It had sound waves moving through it. Yes, sound, though not the kind you could hear. These were pressure waves, oscillations in density and temperature caused by the competition between gravity trying to pull matter together and radiation pressure pushing it apart. Gravity would compress a region, increasing its density. The increased density would create higher pressure, which would push outward, creating a rarefaction, a less dense region. Then gravity would pull again, and the cycle would repeat. These oscillations created pattern-specific sizes and frequencies determined by the physics of the plasma. Scientists call these patterns baryon acoustic oscillations, and we can still see their imprint today in the distribution of galaxies across the sky. The sound waves that rang through the universe in its first few 100,000 years left an echo in the structure of matter, a preferred distance scale that shows up when we measure how galaxies cluster. It's as if the universe remembers the music it played when it was young, and we can still hear the melody written in the stars. But all of this, the plasma, the trapped light, the sound waves, was about to change. The universe was expanding, and expansion meant cooling. The temperature was dropping degree by degree, century by century, millennium by millennium. And there was a critical temperature waiting ahead, a threshold that once crossed would transform everything. That threshold was around 3,000 degrees Kelvin, and it would be reached when the universe was roughly 380,000 years old. At that temperature, something remarkable happened. Electrons, which had been moving too fast to be captured, slowed down enough to be caught by the electric attraction of atomic nuclei. Protons, which are positively charged, pulled in negatively charged electrons. Helium nuclei did the same. And for the first time since the first second, after the Big Bang, complete atoms formed. Hydrogen atoms with one proton and one electron. Helium atoms with 2 protons, 2 neutrons, and 2 electrons. Neutral atoms with no net electric charge, stable and complete. This process didn't happen instantly everywhere. It happened gradually over tens of thousands of years, spreading through the universe as different regions cooled at slightly different rates. But on cosmic scales, it happened fast. And the consequence was immediate and profound. As electrons bound to nuclei, the number of free electrons in the universe plummeted. And without free electrons to scatter them, photons were suddenly free to travel. The fog lifted. The universe became transparent. Light could finally journey across space without interruption. This moment is called recombination, and it marks the end of the plasma era and the beginning of the era we've been exploring, the Dark Ages. The photons that were released at this moment are the photons we detect today as the cosmic microwave background. They've been traveling for nearly 14 billion years, stretched by the expansion of the universe from visible light into microwaves. When we measure the CMB, we're seeing the universe as it was at 380,000 years old, the moment it became transparent the last time light interacted with matter, before streaming freely toward us. But here's the important part for our journey tonight. Even though the universe became transparent, even though light could travel freely, there were no new sources of light being created. The CMB was fading, redshifting, cooling. And there was nothing else. No stars, no galaxies, no quasars, just neutral gas, hydrogen, and helium drifting in the dark, cooling, slowly waiting for gravity to gather it together. The cosmic dawn had happened. The fire of the Big Bang had forged the first elements, but the flames had died down. The universe was entering a long night. A pause. A silence between the violence of creation and the birth of the first stars. And in that silence, in that cooling darkness, the seeds of everything to come were being planted. Tiny variations in density, barely noticeable, but enough. Enough for gravity to notice. Enough to begin the slow gathering that would eventually light the universe again. The fire had been fierce, brief, and total. It created everything we're made of in just 3 minutes. And then it faded, leaving behind a universe full of potential, full of matter, full of possibility, but dark, waiting, patient. The ingredients were ready. The stage was set. Now came the waiting. That waiting we just spoke of, that pause between fire and stars, had a beginning. And that beginning wasn't peaceful. It was a storm of light trapped and furious, unable to escape. For nearly 400,000 years, the universe was drowning in its own brilliance. Think about fog for a moment. Real fog, the kind that rolls in from the ocean on a cool morning. You can be standing in bright daylight, the sun blazing somewhere above you, but you see nothing. The light is there all around you, but it can't reach your eyes in straight lines. It scatters off water droplets bouncing in every direction, creating a soft, diffuse glow that reveals nothing. The early universe was fog, but instead of water droplets scattering sunlight, it was electrons scattering photons. And instead of a few meters of visibility, the distance light could travel before scattering was measured in centimeters, sometimes less. From the very first second after the Big Bang until that moment of recombination, we explored the universe existed in a state we call plasma. This word gets used in different ways. Your blood has plasma. Scientists talk about plasma screens and plasma cutters. But in physics, plasma means something specific. It's the fourth state of matter after solid, liquid, and gas. When you heat a solid, it melts into a liquid. Heat it more, it evaporates into a gas. But keep heating that gas, and eventually the atoms themselves break apart. Electrons get stripped away from their nuclei by the sheer violence of thermal energy. What remains is a soup of charged particles, ions, and free electrons mixed with photons, all interacting electromagnetically with each other. The sun is made of plasma. Lightning creates a thin channel of plasma through the air, which is why it glows so brightly. The aurora borealis, those shimmering curtains of green and red light near Earth's poles, happen when charged particles from the sun interact with plasma in our upper atmosphere. But all of these are tiny, brief local phenomena compared to what the early universe was. Every cubic centimeter of space from one edge of the observable universe to the other was plasma. Not just a little bit, not just in certain regions, everywhere, completely, uniformly. An ocean of plasma stretching in all directions, with no shore, no surface, no escape. And trapped in this ocean was light, more light than you can imagine. For every single proton or neutron in the universe, there were roughly 1 billion photons. Today the universe is matter-dominated. Stars, planets, gas, clouds, dark matter. These things contain most of the energy. But in those first 400,000 years, radiation dominated. The energy in photons outweighed the energy in matter by a vast margin. The universe was fundamentally made of light. Matter was almost an afterthought. But this light couldn't do what light normally does. It couldn't travel freely. Every photon that tried to move forward would slam into a free electron almost immediately. The electron would absorb the photon's energy, jostle around, and then emit another photon in a completely random direction. This process is called Thomson scattering, named after the physicist J.J. Thomson, who studied how light interacts with charged particles in the late 1800s. It's the same physics that makes the sky blue, though on a much more intense scale. Blue light from the sun scatters off molecules in Earth's atmosphere more than red light does, which is why we see blue when we look up. But in the early universe, all wavelengths of light scattered equally off electrons, and they scattered constantly. The mean free path of a photon, the average distance it could travel before hitting an electron, was incredibly small. Scientists estimate it was on the order of centimeters or less. Imagine trying to walk through a crowded room, where every step you take you bump into someone and get turned around to face a random direction. You might be trying to walk north, but after a few steps you're facing east. A few more steps you're facing southwest. You'd wander around essentially at random, never getting very far from where you started, no matter how long you walked. That's what happened to photons in the plasma. They couldn't stream across space. They could only diffuse slowly, chaotically, bouncing from electron to electron. This has a profound consequence. We can't see through the plasma, not because it was dark, but because it was opaque. When we look out into space with telescopes, we're looking back in time. The light from distant galaxies took millions or billions of years to reach us, so we see those galaxies as they were in the past. The farther we look, the further back in time we see. But there's a limit. We can only see back to the moment of recombination, to that time when the plasma cleared and the universe became transparent. Before that, the universe was opaque. Light couldn't travel freely, so there's no light from earlier times that can reach us now. The plasma era is a wall, an impenetrable barrier beyond which we cannot see. This might sound like a limitation, and in some ways it is. We can't directly observe the first 400,000 years of cosmic history with light. But we're not entirely blind. We can observe the consequences. We can measure the cosmic microwave background, which is the afterglow of the plasma, the light that was released when the fog finally lifted. And we can use mathematics and physics to model what must have been happening inside the plasma, even though we can't see it directly. It's like being a detective piecing together what happened in a room you can't enter by examining the evidence left behind. And what the evidence tells us is strange and beautiful. The plasma wasn't still. It wasn't calm. It was ringing like a bell. Sound waves, or more precisely pressure waves, oscillated through the plasma, driven by the competition between two forces. On one side was gravity trying to pull matter together into denser clumps. On the other side was radiation pressure, the force exerted by photons as they bounced off electrons trying to push matter apart. These two forces battled each other, and the result was oscillations. Regions of space would compress under gravity, becoming denser and hotter. The increased pressure would then push outward, creating an expansion. The expansion would go too far, creating a rarefaction, a region less dense than average. Then gravity would pull it back together again, and the cycle would repeat. These oscillations had specific frequencies, specific wavelengths determined by the properties of the plasma. The speed of sound in the plasma depended on temperature and density. The size of the universe at any given moment set limits on which wavelengths could fit. It's similar to how a bell produces specific tones based on its size and composition, not a random jumble of noise. The plasma had its own tones, its own harmonics. Scientists call these baryon acoustic oscillations, and they're one of the most remarkable features of the early universe. We can't hear them directly. Sound doesn't travel through the vacuum of space, and even if it did, these oscillations happened billions of years ago. But we can see their imprint. When the plasma cleared and atoms formed, those oscillations were frozen in place. Regions that happened to be at maximum compression at the moment of recombination had slightly more matter. Regions at maximum expansion had slightly less. These differences were tiny, only about 1 part in 100,000, but they were real. And gravity, patient and relentless, amplified them over billions of years. The denser regions attracted more matter, growing into galaxies and galaxy clusters. The less dense regions became the voids, the empty spaces between structures. When astronomers map the positions of galaxies across the sky today, they find something remarkable. Galaxies aren't distributed randomly. They have a preferred separation distance, a scale, where they tend to cluster more than at other scales. That distance is about 500 million light-years, and it corresponds exactly to the wavelength of the fundamental tone of the baryon acoustic oscillations in the plasma. The universe today still remembers the sound it made when it was young. We can measure that ancient music by counting galaxies. But let's return to the plasma itself, to that ocean of trapped light. What was it like to exist there, if such a thing were possible? First, you would be blind, not because of darkness, but because of brightness. Light would be everywhere, coming from every direction equally. There would be no shadows, no contrasts, no shapes to see. Just a uniform glow, unchanging and featureless. It would be like being inside a light bulb surrounded by radiance but unable to focus on anything. Second, you would feel heat, intense heat. At the beginning of the plasma era, shortly after the first second, the temperature was billions of degrees, hot enough to vaporize anything, hot enough that matter itself couldn't form stable structures. But as time passed, as the universe expanded and cooled, the temperature dropped. By the time of recombination, it had fallen to about 3,000 degrees Kelvin. That's still hot. Hot enough to melt steel, hot enough to glow red-orange if you could see it. But compared to the billions of degrees it started at 3,000, seems almost cool. Third, you would experience no sense of direction. In the plasma, there was no up or down, no north or south. The universe was almost perfectly uniform. Yes, there were tiny fluctuations in density, 1 part in 100,000, but you wouldn't notice them. The plasma looked the same in every direction at every location. It was isotropic, the same everywhere, and homogeneous, the same in all directions. This uniformity is one of the strangest and most important features of the early universe. Why was it so smooth? Why weren't there large random variations in density or temperature? This is one of the problems that the theory of inflation, that brief exponential expansion in the first fraction of a second, was designed to solve. Inflation stretched the universe so rapidly that any irregularities were smoothed out, leaving only the quantum fluctuations that would later seed galaxies. The photons in the plasma weren't just bouncing randomly. They were also in thermal equilibrium with the matter. This means the photons and the electrons and the protons all had the same temperature. They were constantly exchanging energy through collisions, keeping everything at the same average energy level. When a photon hit an electron, it might give the electron energy, making it move faster. Or the electron might give energy to the photon, making it more energetic, shifting its wavelength. These exchanges happened so frequently that the entire system stayed balanced. This equilibrium had a consequence. The spectrum of the radiation, the distribution of photon energies, followed a very specific pattern called a blackbody spectrum. A blackbody is an idealized object that absorbs all radiation that hits it and emits radiation based solely on its temperature. The plasma was very close to a perfect blackbody. And when we measure the cosmic microwave background today, we find that it has an almost perfect blackbody spectrum, one of the most precise blackbody spectra ever measured. This is powerful evidence that the early universe really was in thermal equilibrium, that our models of the plasma are correct. But here's something subtle. Even though the plasma was opaque, even though light couldn't escape, the universe was still expanding. And expansion has an effect on radiation. As space expands, photons get stretched. Their wavelengths increase. This is called redshift, and it happens because the photon's wavelength is tied to the size of space itself. When space doubles in size, wavelengths double, frequencies halve, energies drop by half. This redshift was happening throughout the plasma era. The photons were constantly being stretched by expansion, cooling down, losing energy even as they bounced around trapped in the fog. This gradual cooling is what eventually allowed recombination to happen. The photons started out energetic enough to ionize hydrogen atoms, to knock electrons away from protons, even if they briefly stuck together. But as the universe expanded and the photons redshifted and cooled, there came a point where they no longer had enough energy to ionize hydrogen. At that point, electrons could finally stay bound to protons. Atoms could form and remain stable. And with fewer free electrons to scatter them, photons could finally escape. The fog lifted not because something pushed it away, but because it simply faded as the universe cooled below a critical temperature. There's a common misconception about this era. Some people imagine the early universe as a fiery explosion, like a bomb going off with shrapnel flying outward into empty space. But that's not quite right. The Big Bang wasn't an explosion in space. It was an explosion of space. There was no center, no edge, no empty void surrounding it. The plasma filled all of space, and space itself was expanding, carrying the plasma with it. Every point in space was equivalent. If you were an observer in the plasma, you would see the same thing in every direction. Expansion happening everywhere equally. There was no privileged location, no special vantage point. Another misconception is that the plasma was chaotic, random, turbulent. But it wasn't. It was remarkably smooth and ordered. The sound waves were coherent, following predictable patterns. The temperature variations were tiny and followed statistical rules. The physics governing the plasma is well understood. It's just thermodynamics, electromagnetism, and gravity. The same physics we use to describe gases and plasmas in laboratories today, just applied on a much larger scale and at higher energies. The early universe wasn't mysterious or magical. It followed laws. And those laws have left traces we can measure. For 400,000 years, light swam through this ocean unable to surface. Photons that had been born in the fires of the Big Bang, created in the annihilation of matter and antimatter, or in the primordial fusion reactions, wandered through the plasma scattered billions upon billions of times. They traveled vast distances in total, if you added up all their zigzag paths, but they never got far from where they started, because they had no straight line to follow. They were prisoners of the fog, and the fog was everywhere. But the fog was thinning. With every passing millennium, the temperature dropped a little more. The expansion continued, relentless and patient. The universe was racing toward a threshold. And when it crossed that threshold, when the temperature finally fell below 3,000 degrees, everything changed. The electrons found their nuclei. The atoms formed. The scattering stopped. And the photons, after 400,000 years of wandering, finally ran free. Those photons are still running. They have been traveling for nearly 14 billion years since the fog cleared, stretched and redshifted into microwaves cooled from 3,000 degrees to just 2.7 degrees above absolute zero. But they still carry information. They still tell the story of the plasma encoded in their temperature fluctuations and polarization patterns. When we measure the cosmic microwave background, we're not just seeing an old photograph. We're reading a message written in light, sent from the moment the universe first became transparent. And what that message tells us is that the plasma was ready to let go, ready to release the light, ready to step aside and let the universe become something new. Something darker, yes, but also something with potential. Because in the darkness that followed, gravity could finally work unimpeded. Matter could gather without being blown apart by radiation pressure. Structures could begin to grow. And eventually, after another 100 million years of patient waiting, the first stars would ignite. But the plasma didn't know that. It simply cooled, expanded, and faded, doing what physics demanded, following the laws written into the fabric of reality. And in doing so, it set the stage for everything that would come after. The plasma era wasn't just an obstacle to overcome or a barrier to see through. It was a necessary chapter, a time when the universe learned how to hold light before learning how to make it. A time when everything glowed uniformly before learning to shine in points and patterns. The fog is gone now. The ocean has drained away. But its memory remains encoded in the oldest light we can see, in the statistical patterns of galaxies, in the equations that describe how radiation and matter interact. And as we drift forward from this moment of clearing, from this transition to transparency, we carry with us the knowledge that for a long time longer than most can imagine, the universe was nothing but light and matter mixed together, inseparable, waiting for the moment they could finally part ways and become themselves. The parting we just witnessed, that moment when light and matter finally separated, deserves a closer look. Because in that single transition, in that crossing of a threshold, the universe transformed in ways both obvious and subtle, ways we're still discovering today. 380,000 years. That's how long the universe waited before it could see itself. The transition didn't happen everywhere at once, despite what simplified stories might suggest. The universe is vast, and even though conditions were remarkably uniform, there were tiny variations. Some regions cooled just a bit faster than others. Some reached the critical temperature a few thousand years earlier. Recombination, the process of electrons binding to atomic nuclei, spread through the cosmos like a slow wave, taking tens of thousands of years to complete. Not long on cosmic scales, but not instantaneous either. It was a gentle fade rather than a sharp switch. The temperature that mattered was around 3,000 degrees Kelvin. Below this temperature, electrons move slowly enough to be captured and held by the electromagnetic attraction of protons and helium nuclei. Above it, thermal motion kept them free, moving too fast to be caught. This temperature, 3,000 Kelvin, might seem arbitrary, but it emerges naturally from the physics of hydrogen atoms. The energy needed to ionize a hydrogen atom to strip its electron away is 13.6 electron volts. When you do the mathematics of thermal physics, when you calculate what temperature corresponds to particles having 13.6 electron volts of average kinetic energy, you get roughly 3,000 degrees. The universe didn't choose this temperature randomly. It fell out of the fundamental properties of atoms themselves. As the universe cooled through this threshold, something remarkable happened with the light. For hundreds of thousands of years, photons had been scattering constantly off free electrons, unable to travel more than a few centimeters without colliding. But as electrons combined with nuclei to form neutral atoms, the density of free electrons dropped dramatically. Suddenly, there were far fewer targets for photons to hit. The mean free path the distance a photon could travel before scattering increased from centimeters to kilometers, then to millions of kilometers, then to billions of kilometers, then, effectively, to infinity. Photons could suddenly cross the entire universe without scattering even once. This is what astronomers mean when they say the universe became transparent. Not that it went from dark to light, but that it went from opaque to clear. Light already existed. It was everywhere. But it was trapped, scattered, diffused. After recombination, light could stream freely. It could travel in straight lines. For the first time, if eyes had existed to see, vision would have been possible, though there would have been precious little to see in that dark, empty space. The photons that were released at this moment, the last photons to scatter off electrons before the fog cleared, are the photons we detect today as the cosmic microwave background. They've been traveling toward us for nearly 14 billion years, and they carry information from the moment of their release. When we measure the temperature of the CMB across the sky, we find it's not perfectly uniform. There are tiny fluctuations, hot spots, and cold spots, variations of about 1 part in 100,000. These fluctuations are a map of the density variations in the universe at the moment of recombination. Slightly denser regions had slightly higher temperatures. Slightly less dense regions were slightly cooler. The CMB is like a snapshot frozen at that instant when the universe first became transparent. In 1964, 2 radio astronomers named Arno Penzias and Robert Wilson were working with a large horn antenna at Bell Labs in New Jersey, trying to measure radio signals from the Milky Way. They kept detecting a persistent noise, a background hiss that seemed to come from all directions equally. They thought it might be interference, maybe from New York City, or pigeon droppings inside the antenna. They cleaned the antenna carefully, even removing nesting pigeons, but the signal remained. It was constant, uniform, unchanging. Eventually, they learned that physicists at nearby Princeton University had predicted exactly this sort of radiation as a remnant of the Big Bang. The signal Penzias and Wilson had found wasn't noise. It was the echo of creation itself, the cooled remnant of the plasma era. They had accidentally discovered the cosmic microwave background, and they would later win the Nobel Prize for it. The temperature they measured was about 3 degrees, Kelvin, remarkably close to what theory predicted. Today, with much more precise instruments, we know it's 2.72, 5 degrees above absolute zero. This number isn't random. It's the cooled, red-shifted remnant of the 3,000-degree radiation that was released at recombination. The universe has expanded by a factor of about 1100 since then, stretching all wavelengths by the same factor, reducing all temperatures proportionally. 3000 divided by 1100 is roughly 2.7. The mathematics works. The observation confirms the theory. The universe tells a consistent story. But the CMB doesn't just tell us about temperature. It tells us about geometry, about composition, about the age and fate of the cosmos. When scientists measure the angular size of the fluctuations in the CMB, the typical size of hot spots and cold spots on the sky, they can deduce the curvature of space. Is the universe curved like the surface of a sphere, or saddle-shaped like a mountain pass, or flat, like an infinite sheet of paper? The answer, remarkably, is flat. Within the precision of our measurements, the universe appears to have zero curvature. This flatness is itself a puzzle and a clue, one of the observations that led to the theory of cosmic inflation. The polarization of the CMB photons also carries information. Light waves oscillate, and they can oscillate in different directions. Polarization describes the orientation of those oscillations. When photons scattered off electrons in the plasma, they became polarized in specific patterns depending on the motion of the electrons and the distribution of temperature around them. By measuring these polarization patterns today, astronomers can learn about conditions in the plasma era that wouldn't show up in temperature measurements alone. They can detect the influence of gravitational waves from the earliest moments of the universe, ripples in space-time itself, imprinted on the polarization of light. Recombination also changed the chemistry of the universe in subtle ways. Before recombination, any molecules that tried to form would immediately be torn apart by energetic photons. But after recombination with photons less energetic and atoms more stable, simple molecules could begin to form. Molecular hydrogen H, two hydrogen atoms bonded together, appeared for the first time. This might not sound significant, but molecular hydrogen would later play a crucial role in cooling the first gas clouds that would collapse to form stars. Molecules can radiate away energy more efficiently than individual atoms, and this cooling is necessary for gravity to compress gas into dense enough clumps to ignite fusion. There's a subtlety here worth exploring. The word recombination is technically a misnomer. It implies that electrons and nuclei were combining again, that they had been combined before, but they hadn't. In the plasma, electrons had always been free. They had never been bound to nuclei before this moment. So really, this was the first combination, not a recombination. The term stuck because early physicists studying the process assumed incorrectly that atoms must have existed earlier and then been ionized. By the time the mistake was realized, the name was already standard in textbooks. Science is full of historical accidents like this, names that don't quite match reality, but persist because changing them would cause more confusion than keeping them. After recombination, the universe entered the period we explored at the start of our journey, the Dark Ages. But now we can appreciate what made this darkness different from the opacity that came before. During the plasma era, the universe was opaque but full of light. After recombination, it was transparent but empty of light sources. The distinction matters. Opacity means light exists but can't travel. Darkness means light can travel but doesn't exist. Two very different states, both preventing vision, but for opposite reasons. The transition from one to the other was gradual but consequential. As recombination progressed, as more and more electrons found their nuclei, the scattering rate decreased. Photons that used to scatter millions of times per second started scattering only thousands of times per second, then hundreds, then tens, then for most photons, not at all. The last scattering surface, the moment when the average photon had its final collision with an electron, defines the boundary we see when we look at the CMB. It's not a physical surface, not a shell or a wall, but a moment in time spread across space, marking the transition from opaque to transparent. Imagine being able to watch this transition happen, speeding up time so that millions of years pass in seconds. You would see the universe slowly dimming as the fog thinned, becoming more transparent, but also darker as the sources of light faded. The glow would shift from orange-red toward deeper red, then infrared, then microwaves as the expansion redshifted the light. Eventually, to visible light sensors, the universe would appear completely dark, even though it was flooded with microwave radiation. The disappearance wouldn't be dramatic, no sudden blackout. Just a slow fade to transparency and darkness, like the end of twilight, stretching over millions of years. The neutrality of atoms after recombination also affected how matter interacted with itself. In the plasma, charged particles created electromagnetic fields that influenced each other over long distances. Pressure from radiation kept matter from clumping too efficiently. But once atoms became neutral, electromagnetic forces between them became much weaker. They could only interact through gravity and through direct collisions. This made it much easier for gravity to pull matter together. Density fluctuations that had been oscillating in the plasma, bouncing back and forth between compression and rarefaction, suddenly stopped oscillating. They froze in whatever phase they happened to be in at recombination. Dense regions started to attract more matter. Underdense regions started to empty out. The growth of structure which had been suppressed during the plasma era could finally accelerate. But this growth was still slow. Gravity is a weak force, especially when matter is spread so thinly. The average density of matter in the universe at recombination was only about 1,000 hydrogen atoms per cubic meter. For comparison, the best laboratory vacuums on Earth have about 1,000,000 atoms per cubic meter. Space is empty, and it was even emptier then. For gravity to gather this thin gas into anything substantial required time. Millions of years, tens of millions of years. The seeds were planted at recombination, but they would take a long while to sprout. Scientists study recombination through detailed computer simulations. They start with the known physics of atoms, photons, and gravity plug in the conditions we observe in the CMB, and let the simulation evolve forward in time. These simulations can track billions of particles, watching how they interact, how they clump, how structures grow. And remarkably, when you run these simulations forward to the present day, the universe they produce looks like the real universe we observe. Galaxies form in the right places, with the right sizes, at the right times. This agreement between simulation and observation is one of the strongest confirmations we have that our understanding of recombination and of cosmic history more broadly is fundamentally correct. There's also evidence from a different kind of observation. The oldest stars we can find in the universe have chemical compositions that match what we would expect if they formed from gas that had only been through Big Bang nucleosynthesis. They're made almost entirely of hydrogen and helium, with only trace amounts of heavier elements. This tells us that when those stars formed not long after the Dark Ages ended, the universe hadn't yet been enriched by supernova explosions or other processes that create heavy elements. The gas was still primordial, still carrying the signature of recombination and the earlier fusion in the first 3 minutes. The stars are fossils preserving a record of the conditions from which they formed. The transparency that came with recombination also set a limit on how far back in time we can see with electromagnetic radiation. No matter how powerful our telescopes become, we can't see light from before recombination because there is no light from before recombination that could reach us. The plasma scattered it all. This is sometimes called the cosmic photon barrier, but it's not an absolute limit on observation. Neutrinos, ghostly particles that barely interact with matter, could have escaped from the plasma and even from earlier times. If we could build detectors sensitive enough to catch the cosmic neutrino background, we might see back to just 1 second after the Big Bang. And gravitational waves, ripples in space-time, don't interact with matter at all. They pass through the plasma unimpeded. The polarization patterns in the CMB might carry imprints of gravitational waves from inflation, letting us glimpse the first trillionth of a second long before recombination. For now, though, the CMB remains our earliest direct view of the universe. And What a view it is. A nearly uniform glow, the same temperature in all directions to 1 part in 100,000, with tiny fluctuations that encode the seeds of everything that would come later. The galaxies, the stars, the planets, the atoms in our bodies, all of it traced back to those small ripples in the temperature of the ancient plasma. From uniformity came diversity, from smoothness came structure, from simplicity came complexity. And it all began at that moment of transition when electrons settled into their orbits, when photons streamed free, when the universe took a breath and shifted from one state to another. Recombination wasn't the most dramatic event in cosmic history. No explosions, no violent collisions. Just a gentle cooling a threshold crossed a change of phase. But its consequences rippled forward through all the billions of years that followed. The fog had lifted, the light was free, and the universe for the first time could begin to watch itself evolve. The darkness that followed was not an ending, but a beginning, a canvas waiting for the first brushstrokes of starlight to break the silence and illuminate what had been hidden in the long night. And those first stars, those first lights were already being dreamed into existence in the slow gathering of gas, in the patient pull of gravity, working through the transparent dark. That gathering we just spoke of, that slow pull of gravity through transparent darkness, would define the longest silent chapter in cosmic history, a chapter without witnesses, without light, without anything we would recognize as beautiful. And yet everything that would later shine began here in this emptiness. For over 100 million years, the universe simply waited in the dark. Imagine a library at night after everyone has left. The lights are off. The books sit on their shelves full of stories and knowledge, but no one is there to read them. The potential for wonder exists, but it's dormant sleeping. The dark ages were like that. All the ingredients for stars and galaxies were present scattered through space as neutral hydrogen and helium gas. But nothing was reading them yet. Nothing was activating them. The universe had matter, had energy, had the laws of physics. It just didn't have light. This period began at recombination when the universe was 380,000 years old and lasted until roughly 150 million years after the Big Bang. Some estimates push this number higher to 200 or even 300 million years, depending on how you define the end of the Dark Ages. But the core truth remains the same. For a span of time that dwarfs all of human history, that exceeds the age of the oldest fossils on Earth, the universe existed in absolute darkness. No stars, no galaxies, no quasars, nothing burning, nothing glowing, just gas cooling and drifting in the void. The temperature of this gas tells part of the story. At recombination, when electrons first bound to nuclei, the gas temperature was about 3,000 Kelvin, but the universe was expanding, and expansion cools things. As space stretched, the thermal energy of particles got diluted across larger volumes. The gas temperature dropped steadily, falling from 3,000 degrees to a few hundred, then to tens of degrees above absolute zero. By the end of the Dark Ages, the gas was hovering around 10 or 20, Kelvin barely warmer than the cosmic microwave background itself. Cold, empty, still. But the gas wasn't uniform, even though it was spread remarkably smoothly. The fluctuations we see in the CMB, those 1 part in 100,000 variations in temperature and density, were real. Some regions had slightly more matter than average. Other regions had slightly less. These differences were tiny, barely noticeable. If you could somehow measure the density of gas in 2 neighboring regions, you might find one had 1,001 atoms per cubic meter, and the other had 999, a difference of 2 atoms in 1,000, negligible by any ordinary standard. But gravity doesn't care about ordinary standards. Gravity only cares about mass. And wherever there was even slightly more mass, gravity pulled slightly harder. This is how structure began to grow in the Dark Ages. Not through violent collisions or dramatic events, but through patient accumulation. Dense regions pulling a bit harder attracted gas from their surroundings. As gas fell toward these regions, they became denser still, which increased their gravitational pull, which attracted more gas. It was a positive feedback loop, slow at first, but accelerating over time. The rich got richer, the dense got denser, and the underdense regions losing gas to their denser neighbors became more empty. Scientists call this process gravitational instability, and it's governed by equations that were first worked out in detail by the British physicist James Jeans in the early 1900s. Jeans was studying how clouds of gas behave under their own gravity, and he discovered that there's a critical size. If a gas cloud is larger than this size, called the Jeans length, gravity wins, and the cloud collapses. If it's smaller, pressure wins, and the cloud disperses. The Jeans length depends on temperature and density. Hot gas has a larger Jeans length because pressure is stronger. Dense gas has a smaller Jeans length because gravity is stronger. In the Dark Ages, as the gas cooled, the Jeans length decreased. Smaller and smaller clumps could collapse under their own gravity. But there was a complication. Most of the matter in the universe isn't the kind of matter we're familiar with. It's dark matter, an invisible substance that interacts only through gravity. Dark matter doesn't emit light, doesn't absorb light, doesn't scatter light. It's completely transparent to electromagnetic radiation. We know it exists because we can see its gravitational effects on galaxies and on the large-scale structure of the universe. But we've never directly detected a dark matter particle in a laboratory. And in the Dark Ages, dark matter played the dominant role in structure formation. The reason is subtle but important. Normal matter, the hydrogen and helium gas, can radiate energy. When gas falls into a gravitational well, it heats up from compression and from particles colliding. But then it can cool down by emitting photons, infrared radiation that carries energy away. This cooling allows the gas to collapse further, becoming denser and denser. Dark matter, on the other hand, can't radiate. It can't cool. When dark matter particles fall into a gravitational well, they gain speed, kinetic energy, but they can't get rid of that energy. They stay hot, in a sense, moving rapidly, which prevents them from collapsing into tight, dense cores. So dark matter formed halos, diffuse spherical clouds held together by gravity, but unable to collapse further. And normal matter, the gas, fell into these halos. The dark matter provided the gravitational scaffolding, the framework, and the gas filled in the details. This is the essence of structure formation in the Dark Ages. Dark matter halos grew first through pure gravitational attraction. Then gas collected in these halos, cooled, and began to form denser clumps. Computer simulations of this process reveal something visually striking. If you could watch the Dark Ages unfold in a simulation, speeding up time so that millions of years pass in seconds, you'd see the matter in the universe organizing itself into a pattern called the cosmic web. Dense filaments of dark matter and gas stretching across millions of light years connect to each other at nodes, creating a structure that looks remarkably like neurons in a brain or the mycelium network of fungi. The largest structures, the superclusters of galaxies we see today, began as the nodes in this web. The voids, the empty regions between filaments, were already forming, slowly draining of matter as it flowed toward the denser regions. This cosmic web wasn't created during the Dark Ages. Its seeds were planted much earlier, during inflation, in the first fraction of a second after the Big Bang. But the Dark Ages were when it became visible, when the tiny fluctuations amplified enough to create real significant structures. Gravity was writing the large-scale architecture of the universe, sketching the framework onto which everything else would be built. The gas falling into dark matter halos didn't fall smoothly or uniformly. It followed the filaments of the cosmic web, streaming along these vast highways of matter. At the intersections where filaments met, gas accumulated in dense reservoirs. These reservoirs were the sites where the first stars would eventually form. But during the Dark Ages, they weren't hot enough yet. They were gathering, compressing, growing in mass, but they hadn't reached the critical threshold needed to ignite nuclear fusion. There's a question that sometimes arises. If the Dark Ages were dark, if there were no stars, how do we know what happened? How can astronomers study a time that produced no light? The answer is indirect but clever. We can observe the consequences. We can see the structures that grew during this period, the pattern of galaxy clusters and voids, and work backward to infer what must have happened to produce them. We can also detect the hydrogen gas itself, even though it wasn't emitting visible light. Neutral hydrogen has a special property. Its electron can exist in two slightly different energy states, depending on whether the electron's spin is aligned with the proton's spin or opposite to it. When the electron flips from the higher energy state to the lower, it emits a photon with a very specific wavelength, 21 centimeters. This is called the hydrogen line, and it's one of the most important tools in radio astronomy. During the Dark Ages, neutral hydrogen filled the universe, and in principle, it should have been emitting this 21 centimeter radiation, though very faintly. Astronomers are trying to detect this signal today. The problem is that it's extremely weak and heavily redshifted. The 21 centimeter radiation emitted during the Dark Ages has been stretched by cosmic expansion into radio waves with wavelengths of several meters. And these wavelengths are drowned out by interference from human activity, radio stations, satellites, and electronics. To detect the signal, astronomers need to go to the quietest radio environments on Earth, far from cities or even to the far side of the moon, where Earth itself would block radio noise. It's a challenging observation, but if successful, it would give us a direct view of the Dark Ages, a map of how hydrogen was distributed before the first stars formed. The end of the Dark Ages is defined by the appearance of the first stars, but pinning down exactly when that happened is difficult. Observations of the most distant galaxies we can detect suggest that stars were forming by the time the universe was a few 100 million years old. But those galaxies are not the very first stars. They're collections of millions or billions of stars, which means star formation must have begun earlier, perhaps around 150 million years after the Big Bang, possibly sooner. The first stars themselves were likely solitary or existed in small groups too faint and distant for our current telescopes to see directly. We can only infer their existence from the effects they had on their surroundings. These first stars were different from stars today. Very different. They formed from gas that had never been enriched by previous generations of stars, gas that was pure primordial hydrogen and helium with only trace amounts of lithium. Stars today, even the ones forming right now, in nearby molecular clouds, contain small amounts of heavier elements like carbon, oxygen, and iron elements created by earlier stars and scattered into space by supernova explosions. These heavier elements act as coolants, helping gas clouds radiate away energy and collapse more efficiently. But the first stars had no such help. The only way their gas could cool was through molecular hydrogen H2, which is much less efficient. Because the cooling was inefficient, the gas clouds that formed the first stars had to be much more massive before they could collapse. A star forming today might condense from a cloud with a mass 10 or 100 times that of the Sun. But the first stars required clouds with masses hundreds or even thousands of times the Sun. And when these massive clouds finally did collapse and ignite fusion, the stars they produced were giants. Scientists estimate the first stars called population 3 stars, to distinguish them from later generations, had masses ranging from 100 to several hundred times the mass of the Sun. Such massive stars burn incredibly bright and incredibly hot, but they also burn incredibly fast. A star like our Sun will live for about 10 billion years. A population 3 star with 200 solar masses might live only 2 or 3 million years before exhausting its fuel and exploding as a supernova. They were brief, brilliant candles in the cosmic darkness, living fast and dying young. But their impact would be enormous. When they exploded, they scattered the first heavy elements into space, enriching the gas and making it easier for the next generation of stars to form. They were cosmic pioneers, transforming the universe from a place that had never known light into a place where light would become commonplace. The Dark Ages were not a mistake or a delay. They were a necessary phase, a time for the universe to organize itself, to let gravity do its slow work of gathering matter into the configurations that would allow stars to form. Without this period of cooling and clumping, without the patient accumulation of gas in dark matter, halos, the first stars, could never have ignited. Darkness enabled light. Silence prepared for sound. Emptiness made space for creation. And perhaps there's something humbling in that. The idea that the most important transformations sometimes happen in the dark, unseen, unwitnessed. That the preparations for beauty can take far longer than the beauty itself. The Dark Ages lasted 100 million years. The first stars burned for only a few million. But those few million years of light depended entirely on the 100 million years of darkness that came before. The universe was learning patience, learning to wait, learning to let small differences compound over time into large structures. And in that, waiting in that compounding, the seeds of galaxies were sprouting invisible roots spreading through the dark, preparing to bloom into light. The canvas was ready. The stage was set. And the first actors were about to make their entrance, stepping into a theater that had been empty since the beginning, ready to illuminate what had been hidden, to reveal what had been gathering in the long, silent night. Those seeds we just mentioned, those invisible roots spreading through the darkness, had an origin so small and so early that it strains imagination. The galaxies spinning above us tonight, the clusters and superclusters spanning billions of light years, all began as quantum fluctuations in the first trillionth of a second after the Big Bang. The universe was born from uncertainty itself. Quantum mechanics tells us that at the smallest scales, nothing is perfectly smooth. Energy fluctuates randomly, popping in and out of existence, creating tiny ripples in the fabric of space-time. These fluctuations are usually microscopic, confined to distances smaller than atoms, and they average out to zero over time. But during inflation, that brief period of exponential expansion we touched on earlier, something remarkable happened. The universe expanded so rapidly that quantum fluctuations got stretched to cosmic sizes before they could average out. Ripples smaller than a proton became ripples spanning light years, then millions of light years, then billions. These stretched quantum fluctuations became the seeds of structure. Regions where the fluctuation added a tiny bit of extra energy became slightly denser. Regions where it subtracted energy became slightly less dense. The differences were minuscule, 1 part in 100,000, but they were real. And they were frozen into the fabric of space, locked in place by the expansion unable to smooth out. When inflation ended and the universe transitioned into the normal expansion we still observe today, these fluctuations remained embedded in the distribution of matter and energy. Scientists can calculate the statistical properties of these fluctuations using quantum field theory, the mathematics that describes how particles and fields behave at the smallest scales. And when they do these calculations, they predict a specific pattern. Fluctuations should exist at all scales, but with different amplitudes. Larger scales should have slightly stronger fluctuations than smaller scales, following a relationship described by what's called a scale invariant spectrum, with a slight tilt. This is technical language for a simple idea. Big ripples in small ripples, with the big ones slightly more pronounced. When astronomers measure the temperature fluctuations in the cosmic microwave background, they find exactly this pattern. The statistics match the predictions from quantum field theory during inflation. This agreement is one of the most profound confirmations in all of physics. It tells us that the largest structures we can observe, galaxy clusters spanning hundreds of millions of light years, originated from quantum mechanical processes occurring at scales a billion times smaller in the first instant of cosmic time. The very big and the very small connected by the expansion of space itself. But these seeds didn't just sit there unchanged. They grew. And the way they grew depended on what was happening in the universe at different times. During the plasma era, remember, radiation dominated. Photons carried most of the energy, and they created pressure that resisted the pull of gravity. Fluctuations in normal matter. The hydrogen and helium tried to collapse under their own gravity, but radiation pressure pushed back. The result was oscillation. The baryon acoustic oscillations we discussed earlier. Regions compressed, expanded, compressed again, creating sound waves in the plasma. But dark matter didn't interact with photons. It felt gravity, but not radiation pressure. So, while normal matter was oscillating, dark matter was quietly collapsing, growing denser in the regions where the initial seeds were strongest. By the time of recombination, dark matter had already formed halos, gravitational wells into which normal matter could fall once it decoupled from radiation. This head start is crucial. Dark matter provided the framework, the skeleton onto which normal matter could attach and condense. After recombination, once the universe became transparent and matter-dominated, the growth of structure accelerated. Without radiation pressure to resist, collapsed gas could fall freely into the dark matter halos. The deeper the halo, the more mass it contained, the faster gas accumulated. And as gas fell inward, it collided with other gas heating up from the compression and from friction. In the deepest halos where the most mass had gathered, the gas heated to temperatures of thousands of degrees, maybe tens of thousands. This heating created a problem for star formation. Hot gas has high pressure, which resists further collapse. For a cloud of gas to continue collapsing and eventually ignite fusion, it needs to cool down to radiate away the thermal energy it gains from compression. Stars today form in molecular clouds that contain dust and molecules like carbon monoxide and water vapor. These molecules are excellent coolants. They absorb thermal energy and re-emit it as infrared radiation, carrying heat away efficiently. But the primordial gas in the dark ages had no such molecules. No dust, no carbon monoxide, no water vapor, just hydrogen and helium and traces of lithium. The only available coolant was molecular hydrogen H2. When two hydrogen atoms collide, they can sometimes stick together to form a molecule. And molecular hydrogen, unlike atomic hydrogen, can radiate infrared light, cooling the gas. But the process is inefficient. Molecular hydrogen forms slowly and radiates weakly compared to the heavy molecules in modern star-forming clouds. This inefficiency meant that primordial gas clouds had to become much hotter and much denser before they could cool enough to collapse into stars. The mass required is estimated at around 100,000 to 1 million times the mass of the Sun. These were the first clouds massive enough to overcome the lack of efficient cooling, to compress and heat and cool and compress, again spiraling inward under their own gravity, until the center became dense enough and hot enough for nuclear fusion to ignite. And when fusion finally did ignite, the stars that formed were massive, very massive. Scientists estimate they range from 100 to 300 solar masses, with some models suggesting even larger masses were possible. Why so massive? The answer lies in the cooling rate. In a cloud that cools slowly, gravity has time to pull in more and more material before the center gets dense enough to halt the collapse by forming a star. The cloud fragments less, creating fewer but more massive stars. Modern star-forming clouds with their efficient dust and molecular coolants fragment into many pieces, creating stars of all masses from tiny red dwarfs, a tenth the mass of the Sun, to rare giants 20 or 30 solar masses. But the primordial clouds cooling slowly through molecular hydrogen alone tended to form just one or a few massive stars per cloud. These massive first stars, the population 3 stars, would have been extraordinary objects. Their surfaces glowed blue-white, far hotter than the Sun's yellow surface. The Sun has a surface temperature around 5,800 Kelvin. A population 3 star might reach 100,000 Kelvin, radiating mostly in ultraviolet light. They were intensely bright, perhaps 1,000,000 times more luminous than the Sun, burning through their nuclear fuel at a ferocious rate. Inside these stars, fusion proceeded through a chain of reactions. hydrogen fused into helium, as in normal stars. But in the hottest cores, helium fused into carbon-carbon, into oxygen-oxygen, into neon and magnesium, and on through silicon all the way to iron. Elements that didn't exist before, created for the first time in the universe inside these stellar furnaces. The periodic table was being written one fusion reaction at a time in the hearts of stars that had never seen a previous generation. But iron is the end of the line for fusion. Fusing elements heavier than iron consumes energy rather than releasing it. So, when a population 3 star's core filled with iron, fusion stopped. The core, no longer supported by the outward pressure from fusion reactions, collapsed catastrophically. In less than a second, a core the size of Earth compressed into a neutron star or black hole only kilometers across. The outer layers of the star, suddenly losing the support from below, fell inward at a significant fraction of the speed of light. Then they rebounded, smashing outward in a supernova explosion, one of the most violent events in nature. The explosion released more energy in a few seconds than the star had emitted in its entire lifetime. It created a shock wave that blasted through space heating gas to billions of degrees, and it scattered all the elements the star had created, carbon and oxygen and silicon and iron, into the surrounding interstellar medium. This was the first time heavy elements existed outside a star, the first time the universe had carbon for building organic molecules, oxygen for water iron for rock and metal. These elements would mix with the primordial hydrogen and helium, enriching the gas, making it easier for the next generation of stars to cool and form. The supernova also released neutrinos, vast numbers of ghostly particles that barely interact with matter. In fact, most of the energy from the core collapse goes into neutrinos, not light. These neutrinos streamed outward at nearly the speed of light, passing through the star's outer layers, as if they weren't there carrying away information about the core's final moments. If we could detect neutrinos from a population 3 supernova today, we could learn about the death of these first stars directly. But they're too distant, too faint, and too redshifted for current neutrino detectors to see. The explosions may have also triggered the formation of new stars. Shock waves from supernovae can compress nearby gas clouds, pushing them over the threshold needed to collapse. A single population 3 star dying violently might have seeded the formation of dozens or hundreds of second-generation stars in the enriched gas around it. This is how star formation can become self-sustaining, each generation enabling the next building up, from isolated giants to clusters to galaxies. The timeline of these events is still uncertain. We know the first stars must have formed sometime between 100 and 400 million years after the Big Bang, but pinning down a more precise date is difficult. The most distant galaxies we've observed with telescopes like the Hubble and the James Webb Space Telescope existed when the universe was around 400 million years old. These galaxies already contained millions of stars, which means star formation must have begun earlier. But individual population 3 stars are too faint and too distant to see directly with current technology. There's an indirect way to detect their influence, though. When the first stars turned on, their ultraviolet radiation began to ionize the hydrogen gas around them. Ultraviolet photons have enough energy to strip electrons away from hydrogen atoms, turning neutral hydrogen into ionized hydrogen. This process created bubbles of ionized gas surrounding each star or small group of stars. At first, these bubbles were tiny isolated islands in a sea of neutral hydrogen, but as more stars formed, the bubbles grew and merged, gradually ionizing larger and larger volumes of space. This process, called reionization, marked the end of the Dark Ages and the beginning of a new era. We'll explore it more deeply soon, but for now, it's enough to know that the seeds we've been following, the quantum fluctuations from inflation, guided not just the formation of stars, but the entire architecture of the cosmos. The pattern of fluctuations determined where dark matter halos formed. The halos determined where gas collected. The gas determined where stars ignited. and the stars determine how the universe would be transformed from a neutral, dark, quiet place into the ionized, luminous, dynamic universe we inhabit today. Scientists study these seeds using computer simulations that track billions of particles from the early universe to the present. These simulations start with the fluctuations measured in the CMB and evolve them forward using the known laws of gravity fluid dynamics and thermodynamics. The simulations can show how dark matter halos merge and grow, how gas flows along filaments, how stars form and explode, and how galaxies assemble over billions of years. When the simulations reach the present day, they produce a universe that looks remarkably like the real one. The distribution of galaxies, the sizes of clusters, the shapes of voids all match observations. This agreement gives us confidence that we understand the broad strokes of structure formation, even if many details remain uncertain. One of the beautiful aspects of this story is the connection across scales. The seeds were quantum mechanical operating at scales where uncertainty dominates. They were stretched to cosmic scales by inflation, a process driven by quantum fields and general relativity. They grew through gravitational instability, governed by Newton's laws on small scales and Einstein's on large. They ignited fusion, a nuclear process, and they created the chemical elements through supernova nucleosynthesis, another nuclear process. Quantum mechanics, relativity, gravity, thermodynamics, nuclear physics all played essential roles. The universe is one story told in many languages, and we are part of that story. The carbon in our cells, the oxygen we breathe, the calcium in our bones, all of it was created in stars. Some of it in the first stars, the population 3 giants that lived and died in the Dark Ages. Most of it in later generations in stars, more like the sun that lived longer and died more gently, scattering their elements through stellar winds and planetary nebulae. But the chain began with those first massive stars, the ones that dared to shine in a universe that had never known light, that took the seeds planted by quantum fluctuations and turned them into the building blocks of everything we see. The cosmic web, the filaments and nodes, the voids and clusters, all of it traces back to those initial ripples. And those ripples trace back to the uncertainty principle, to the fundamental quantum fuzziness that prevents the universe from being perfectly smooth. In a strange way, we owe our existence to uncertainty, to randomness, to the fact that nature refuses to be perfectly predictable at the smallest scales. Without quantum fluctuations, the universe would have stayed smooth, uniform, featureless. No stars, no galaxies, no planets, no life. The seeds of everything were planted in chaos in the random jitter of quantum fields, amplified by cosmic expansion into the garden we now inhabit. And as those seeds sprouted, as dark matter gathered and gas flowed and stars began to burn, the universe was crossing a threshold, stepping from its long night into a new dawn. A dawn that would wash over the cosmos in waves of ultraviolet light, transforming neutral hydrogen into plasma once again, but this time from the inside out, star by star, bubble by bubble, until the entire universe glowed with the light of a billion suns. That dawn we just glimpsed those bubbles of light beginning to spread started with a single moment. One cloud of gas somewhere in the dark universe crossed a threshold, and for the first time in over 100 million years, light returned to the cosmos. The first star didn't announce itself. It simply began. Imagine the loneliness of that moment. For all the time since recombination, the universe had been dark, cold, silent. Gas drifting in invisible halos pulled by invisible dark matter, cooling slowly in the void. And then in one small region, perhaps just a few light years across, the temperature and density reach critical values. The core of a gas cloud, compressed by gravity to unimaginable densities, heated to 10 million degrees. At that temperature, hydrogen nuclei moving fast enough to overcome their electromagnetic repulsion collided and fused. 4 hydrogen nuclei became 1 helium nucleus, and the difference in mass, that tiny fraction lost in the fusion, converted into energy according to Einstein's equation, E equals mc squared. Light poured out of the core, the first light, the first star. We don't know exactly when this happened. The best estimates place it somewhere between 100 and 200 million years after the Big Bang, though some models suggest it could have been as early as 50 million years or as late as 400 million. The uncertainty comes from how difficult it is to observe this era directly. We can see distant galaxies that existed a few 100 million years after the Big Bang, but individual stars from that time are too faint too far away. Their light too redshifted for our current telescopes to detect them individually. We know they must have existed because we see their collective effects, the galaxies they built, the elements they scattered. But the stars themselves remain hidden, visible only in the mathematics and simulations that describe their birth. Those simulations paint a consistent picture, though. The first stars were not like the sun. They were giants, behemoths, monsters of fusion burning 100 or 200 or even 300 times more massive than our modest solar companion. Why so massive? The answer lies in the purity of the gas from which they formed. That gas was pristine, untouched by previous generations of stars. No carbon, no oxygen, no silicon or iron. Just hydrogen, helium, and the faintest whisper of lithium left over from Big Bang nucleosynthesis. And without heavier elements, the gas couldn't cool efficiently. Cooling is essential for star formation. When gas collapses under gravity, it heats up from compression. If it can't radiate that heat away, pressure builds up and halts the collapse before the core becomes dense enough for fusion. Modern stars form in molecular clouds rich with dust grains and complex molecules. Carbon monoxide, water, vapor, ammonia. These molecules absorb thermal energy and re-emit it as infrared photons carrying heat away. But primordial gas had none of these. The only coolant available was molecular hydrogen H2, and it radiates far less efficiently than modern coolants. Because the cooling was slow, the collapsing cloud had time to pull in more and more gas before the center became dense enough to form a star. Instead of fragmenting into many small stars, the cloud tended to form just one massive star, or perhaps a tight binary pair. And when that star finally ignited fusion, the energy release was extraordinary. A star 200 times, the mass of the sun doesn't shine 200 times brighter. It shines closer to 1,000,000 times brighter. The relationship between mass and luminosity is steep for massive stars. More mass means higher core temperature, which means faster fusion, which means vastly more energy output. The surface of such a star would glow blue-white, radiating most of its energy in ultraviolet light. The temperature at the surface might reach 100,000 Kelvin compared to the sun's 6,000. If you could somehow stand near a population 3 star, not that anything could survive, but if you could, you wouldn't see it as blue. You'd see it as blinding ultraviolet, invisible to human eyes, but intense enough to ionize atoms and break apart molecules from millions of miles away. These stars were ultraviolet furnaces pumping out photons energetic enough to strip electrons from hydrogen atoms across vast distances. Inside the star, the core burned at temperatures exceeding 100 million degrees. At these temperatures, fusion didn't stop at helium. The CNO cycle, which requires carbon, nitrogen, and oxygen, couldn't operate because those elements didn't exist yet. But the proton-proton chain, the simplest fusion pathway, ran at full speed. 4 hydrogen nuclei fused into helium, releasing energy. As the star aged and helium accumulated in the core contracted and heated further. Eventually, helium itself began to fuse, creating carbon and oxygen through a process called helium burning, or the triple alpha process. 3 helium nuclei, each containing 2 protons and 2 neutrons, combine to form 1 carbon nucleus. Sometimes a 4th helium nucleus adds to make oxygen, and the fusion didn't stop there. In the most massive population 3 stars, the cores became hot enough for carbon to fuse into neon and magnesium. Neon fused into oxygen and magnesium, oxygen into silicon and sulfur, silicon into iron and nickel. Each stage of fusion released energy supporting the star against gravity, but each stage also proceeded faster than the last. Hydrogen burning might last a few million years, helium burning a few 100,000, carbon burning a few thousand years, silicon burning just a few days. The star was racing through the periodic table, creating elements that had never existed before, building up the chemical diversity that would later make planets and life possible. But iron is a dead end. Iron has the most stable nucleus of any element. Fusing it into heavier elements requires energy input rather than releasing energy. So, when the core filled with iron, fusion stopped. The core, no longer generating heat and pressure to support itself against gravity, collapsed. And it collapsed fast. In less than a second, a core the size of Earth compressed into a ball only 20 kilometers across. Protons and electrons, crushed together by gravity, merged into neutrons. The core became a neutron star so dense that a teaspoon of its material would weigh 1 billion tons. The outer layers of the star, suddenly losing the support from below, fell inward at speeds approaching 1/4 of the speed of light. When they hit the incompressibly dense neutron core, they rebounded, creating a shock wave that blasted outward through the star. This shock wave, carrying more energy than the star had radiated in its entire lifetime, ripped the star apart in a supernova explosion. The explosion released about 10 to the 46 joules of energy. To put that in perspective, if you could somehow capture all the energy the sun will emit over its entire 10 billion year life and release it in 1 second, that's roughly the energy of a supernova. It's almost incomprehensible. The light from the explosion would have been visible across millions of light years, if there had been eyes to see it. For a few weeks, the supernova would outshine all the other stars in its vicinity, combined a brilliant point of light, fading slowly back into darkness. But the light was only part of the story. The explosion also created heavy elements through a different process called explosive nucleosynthesis. The intense heat and neutron flux in the shock wave allowed rapid neutron capture, building elements heavier than iron, gold, platinum, uranium. All the elements that can't be made by normal fusion formed in those few seconds of violence. And all of it, all the carbon and oxygen and silicon and iron and gold, blasted into space, mixing with the primordial hydrogen and helium. This enrichment changed everything. The next generation of gas clouds that collapsed to form stars would have trace amounts of heavy elements. Not much, maybe 1 part in 100,000, but enough. Carbon and oxygen could form molecules like carbon monoxide and water vapor. Dust grains could condense. And these molecules and grains would cool the gas far more efficiently than molecular hydrogen alone. The clouds could fragment into smaller pieces. Stars of lower mass could form. The universe was learning to make stars like the sun's stars, with long lifespans measured in billions of years, stars stable enough to host planets where life might eventually emerge. Scientists classify stars into populations based on their metal content, where metal, in astronomy, means any element heavier than helium. Population 1 stars like the sun are relatively metal-rich, containing about 2% heavy elements by mass. They're young stars formed recently from gas, enriched by many generations of supernovae. Population 2 stars are metal-poor, containing perhaps 1/10 or 100th as much formed from gas, enriched by only a few generations. And population 3 stars, the first stars, are metal-free or nearly so. None have ever been observed directly because they all died billions of years ago. But we've found extremely metal-poor stars, 2nd or 3rd generation, stars formed from gas, barely enriched by the first supernovae, and they give us clues about what the population 3 stars must have been like. One such star, discovered in the halo of our own Milky Way galaxy, has less than 1/10 millionth the iron content of the sun. It's likely a second-generation star formed from gas enriched by a single population 3 supernova. By studying its chemical composition, astronomers can infer the properties of the supernova that enriched its birth cloud. How massive was the progenitor star? How did it explode? What elements did it create? Each ancient metal-poor star is a fossil, preserving a chemical fingerprint of the early universe. The first stars were probably solitary or existed in very small groups. The massive clouds that formed them didn't fragment much, so you might have 1 or 2 or 3 massive stars per dark matter halo. This is very different from modern star formation, where clouds fragment into clusters containing hundreds or thousands of stars of varying masses. But even though population 3 stars were rare, their impact was enormous. Each one that exploded enriched the gas around it, triggered new star formation through shock waves, and contributed to the ionization of the universe. There's a possibility suggested by some theoretical models that a few of the most massive population 3 stars didn't explode as supernovae. If the core was massive enough, more than about 50 solar masses, the collapse might not produce a rebound. Instead, the entire star could collapse directly into a black hole without an explosion, a process called direct collapse. No fireworks, no scattering of elements, just a star winking out, leaving behind a black hole as its only remnant. If this happened, it could explain the origin of the supermassive black holes we observe at the centers of galaxies. Perhaps some of them started as population 3 stars that collapsed directly, then grew over billions of years by accreting matter and merging with other black holes. The lifespan of a population 3 star was short, brutally short. A star 200 times the mass of the Sun might live only 2 million years from birth to supernova. For comparison, the Sun will live about 10 billion years, 5,000 times longer. Population 3 stars lived, fast burned bright, and died young, leaving behind neutron stars or black holes and a legacy of heavy elements. They were the phoenixes of the cosmos, dying so that future generations could be born from their ashes. And they were loud in a sense, not in sound which can't travel through the vacuum of space, but in gravitational waves. When a massive star collapses and explodes, when a black hole forms, space-time itself ripples. These ripples, gravitational waves, propagate outward at the speed of light, carrying information about the violent events that created them. We've detected gravitational waves from black hole mergers and neutron-star collisions in the modern universe using observatories like LIGO and Virgo. Someday, perhaps, with future space-based detectors, we might detect gravitational waves from population 3 supernovae or black hole formations, giving us a direct window into the deaths of the first stars. The universe during this era was transforming rapidly. Each new star that ignited added its light to the growing cosmic glow. Each supernova enriched more gas, making it easier for the next generation of stars to form. It was a runaway process, an exponential growth in the number of stars and the brightness of the universe. From complete darkness to scattered points of light, to clusters, to the beginnings of galaxies, all in a few 100 million years. Fast on cosmic timescales, but still incomprehensibly slow by human measures. And with each star came ionization. Ultraviolet photons from the stars didn't just travel outward. They interacted with the neutral hydrogen gas filling the space between stars. Each ultraviolet photon with enough energy, more than 13. 6 electron volts could ionize a hydrogen atom, stripping its electron away. Around each star, a bubble of ionized hydrogen grew, expanding outward at the speed of light until the photons were all absorbed. At first, these bubbles were small and isolated islands of ionization in a neutral sea. But as more stars formed, the bubbles overlapped and merged, creating larger ionized regions. This process, the gradual ionization of the universe by starlight, is called the epoch of reionization. And it would fundamentally change the state of the cosmos, returning it to a plasma much like the early universe. But from the inside out, carved by stars rather than cooled by expansion. The first stars were torches in the dark, brief and bright, lighting a path for everything that would follow. They transformed a universe of pure hydrogen and helium into one with the chemical diversity needed for rocky planets and liquid water and complex molecules. They were the spark that lit the fire that still burns in every star we see tonight. And though we can't see them directly, though they died billions of years before, the Earth formed, their influence surrounds us. Every breath you take contains oxygen forged in their cores. Every beat of your heart depends on iron they scattered into space. We are quite literally made of the ashes of the first stars, children of the primordial giants who dared to shine in the dark. That transformation we just touched on, those bubbles of ionized gas expanding around each new star, would eventually consume the entire universe. The neutral hydrogen that had dominated for hundreds of millions of years was about to surrender to light. And in that surrender, the cosmos would become transparent in a new way, opening itself to radiation that had been absorbed for eons. The universe was waking up star by star, bubble by bubble, slowly at first, then all at once. Rionization is a deceptively simple word for an extraordinarily complex process. The basic idea is straightforward. Ultraviolet photons from stars strike neutral hydrogen atoms, transferring enough energy to strip the electron away, leaving behind a bare proton and a free electron. The hydrogen atom, which had been neutral since recombination, becomes ionized again, returning to the plasma state it had known in the first few 100,000 years after the Big Bang. But this time, the ionization happened from the inside out, carved by stars rather than from the outside in, cooled by expansion. Each population 3 star, blazing with ultraviolet fury, created an ionization bubble around itself. The size of the bubble depended on how many ionizing photons the star produced and how dense the surrounding hydrogen was. A typical bubble might span a few thousand light years, initially a small sphere of ionized plasma in a vast ocean of neutral gas. As long as the star kept shining, the bubble kept growing, expanding outward at nearly the speed of light as photons raced ahead, ionizing hydrogen as they went. But there was resistance. Ionized hydrogen doesn't stay ionized forever. Free electrons and protons left alone will eventually recombine, forming neutral hydrogen atoms again. This recombination happens faster in denser regions where electrons and protons encounter each other more frequently. So, the star had to work continuously producing ionizing photons, not just to expand its bubble but to maintain the ionization of hydrogen it had already ionized. It was like trying to empty a leaking bucket. You can pour water out, but if the leak is too fast, the bucket never empties. In the low-density intergalactic medium, the medium between galaxies where most of the universe's hydrogen resided, recombination was slow. An ionized region could stay ionized for millions of years before recombining. But in denser regions near the star itself, or in gas clouds, recombination was much faster. The star had to overpower the recombination rate to keep its bubble inflated. And when the star died, when it exploded as a supernova or collapsed into a black hole, the ionizing radiation stopped. The bubble stopped growing. And over time, neutral hydrogen would seep back in from the edges, reclaiming the space. But if another star formed nearby before the bubble collapsed, if its bubble overlapped with the first star's bubble, the combined ionized region would be larger and more stable. 2 stars could maintain a bigger bubble than either could alone. And if a third star formed, and a fourth, and eventually hundreds or thousands clustering together in what would become the first galaxies, the ionized regions would grow enormous, spanning millions of light years. These megabubbles, powered by entire galaxies worth of stars, could resist recombination and expand outward, eating into the neutral hydrogen around them. The epoch of rionization, the period when this process transformed the universe, lasted from roughly 150 million years after the Big Bang to about 1 billion years. That's a span of 850 million years, during which the universe gradually shifted from mostly neutral to almost completely ionized. Scientists divide this era into three phases: the pre-overlap phase, when bubbles were isolated islands in a neutral sea; the overlap phase, when bubbles began to merge, and neutral regions became isolated islands in an ionized sea; and the post-overlap phase, when the last neutral regions were ionized, and the universe became fully transparent to ultraviolet light. Observations suggest that reionization was about half complete when the universe was around 700 million years old. By 1 billion years, it was essentially finished, though pockets of neutral hydrogen persisted in dense regions for a while longer. The exact timeline is still uncertain because reionization is difficult to observe directly. We can't see neutral hydrogen easily at these distances and redshifts, but we can infer its presence from how it absorbs light from distant quasars. Quasars are extremely bright objects powered by supermassive black holes at the centers of galaxies. They emit vast amounts of light across all wavelengths, including ultraviolet. When that light travels through space toward us, it passes through any intervening hydrogen gas. Neutral hydrogen absorbs light at specific wavelengths corresponding to its electron transitions. The strongest absorption happens at the Lyman alpha line, 121.6 nanometers. The wavelength emitted when an electron in hydrogen drops from the second energy level to the first. If the universe is mostly neutral, light from a distant quasar will be heavily absorbed by all the hydrogen between the quasar and us. The spectrum of the quasar will show a deep trough at wavelengths shorter than Lyman alpha, called the Gunn-Peterson trough, named after the astronomers who predicted it in the 1960s. If the universe is mostly ionized, there's very little neutral hydrogen to absorb the light and the trough disappears. By measuring the depth of the Gunn-Peterson trough in spectra of high redshift quasars, astronomers can estimate how much neutral hydrogen existed at different times in cosmic history. The results show a clear transition. Quasars at redshift greater than 6, corresponding to times less than 1 billion years after the Big Bang, show strong Gunn-Peterson absorption, indicating significant neutral hydrogen. Quasars at lower redshifts show little or no absorption, indicating the universe had become mostly ionized. The transition is gradual, not sharp, consistent with a reionization process that happened over hundreds of millions of years, progressing unevenly across different regions of space. There's also evidence from the cosmic microwave background. When the universe reionized, the free electrons created by ionization could scatter CMB photons, just as electrons in the early plasma had scattered them before recombination. This scattering changes the polarization of the CMB in subtle ways. By measuring these polarization signatures, scientists can estimate when reionization occurred and how long it lasted. The data from satellites like WMAP and Planck suggest that reionization began around redshift 15 or 20, corresponding to 150 to 200 million years after the Big Bang, and was mostly complete by redshift 6 around 1 billion years. But what actually drove reionization? What produced all those ionizing photons? The answer is mostly stars, but not just population 3 stars. By the time reionization was in full swing, second and third generation, stars were forming enriched by the heavy elements from earlier supernovae. These stars were smaller on average than population 3 stars, more like 10 to 100 solar masses rather than hundreds, but they were vastly more numerous, and collectively, they produced an enormous flux of ultraviolet radiation. There's a catch, though. Stars don't emit all their light as ionizing ultraviolet. Much of the energy goes into longer wavelengths that can't ionize hydrogen, and some of the ionizing photons get absorbed by gas and dust near the star before they can escape into intergalactic space. The fraction of ionizing photons that escape, called the escape fraction, is a critical parameter in reionization models. If the escape fraction is high, stars can efficiently ionize the universe. If it's low, you need many more stars to do the job. Observations of nearby star-forming galaxies suggest escape fractions around 10 to 20%, though this varies widely depending on the galaxy's structure and how much dust it contains. Early galaxies with less dust and more porous structures might have had higher escape fractions, maybe 30 or even 50%. But this is still uncertain. It's one of the biggest unknowns in reionization theory. Quasars also contributed to reionization. Supermassive black holes accreting matter emit intense ultraviolet and X-ray radiation, and some of this can ionize hydrogen. But quasars were probably less important than stars for most of the reionization process. They were rare at early times, and they tended to be clustered in overdense regions rather than spread uniformly. Stars were more numerous and more evenly distributed, making them the primary drivers of the global ionization. Reionization wasn't just about changing the ionization state of hydrogen, it also heated the gas. When an ultraviolet photon ionizes a hydrogen atom, any excess energy beyond the 13.6 electron volts needed for ionization goes into kinetic energy of the freed electron. That electron then collides with other particles sharing its energy heating the gas. The temperature of the intergalactic medium rose from around 10 Kelvin before reionization to 10,000 Kelvin or more afterward. That's a 1,000-fold increase in temperature enough to significantly affect how gas behaved. Hot gas has higher pressure, which makes it harder for gravity to pull it together. This heating suppressed star formation in small, dark matter halos. Before reionization, halos with masses as low as 1 million solar masses could cool their gas and form stars. After reionization, only halos with masses above about 100 million or 1 billion solar masses could overcome the increased pressure and continue forming stars. The smallest galaxies were effectively shut down, prevented from growing by the very process their predecessors had initiated. This is an example of what's called feedback, where star formation changes the conditions for future star formation. Stellar feedback operates on multiple scales. Individual supernovae heat and disperse nearby gas, temporarily halting star formation in their vicinity. Clusters of stars create winds of hot gas that can blow out of galaxies, entirely carrying away the raw material for future stars. And the collective effect of many galaxies reionizing and heating the intergalactic medium changes the global rate of star formation across the universe. Feedback is essential for understanding why galaxies have the masses and star formation rates they do. Without it, simulations predict galaxies would form too many stars too quickly, converting all their gas into stars within a few 100 million years. Feedback slows things down, making galaxy formation a gradual, self-regulated process. There's a poetic irony in reionization. The same stars that illuminated the dark universe also made it harder for new stars to form. They opened the door to a new era, but in doing so, they closed certain paths. The universe gained light, but lost some of its potential for future creation. It's a reminder that growth and change often involve trade-offs that progress in one direction can foreclose possibilities in another. The end of reionization marked the end of the universe's dark age and the beginning of what some call the Age of Galaxies. By 1 billion years after the Big Bang, the cosmos looked fundamentally different than it had at 400 million years. Instead of scattered pockets of light in overwhelming darkness, there were scattered pockets of darkness in overwhelming light. The flip had occurred. The transition was complete. And from that point forward, the universe would remain mostly ionized, transparent to ultraviolet light, illuminated by an ever-growing population of stars and galaxies. We live in the aftermath of reionization. The hydrogen around us between galaxies and the outskirts of clusters is ionized. It's a thin plasma so tenuous that we usually ignore it. But it's there maintained in its ionized state by the continued production of ultraviolet light from stars and quasars. If every star in the universe suddenly turned off, if all the quasars went dark, the intergalactic medium would slowly recombine over hundreds of millions of years, becoming neutral again. But that won't happen. Stars will keep forming, black holes will keep accreting, and the universe will stay awake, kept in its ionized state by the restless energy of fusion and gravity. Ionization also made the universe more homogeneous, in a sense. Before, neutral regions and ionized regions had very different properties, different temperatures, different abilities to cool and form stars. After, almost everywhere was ionized. Almost everywhere had similar temperature and density, at least on large scales. The cosmic web was still there, the filaments and voids, but the hydrogen filling those structures was uniformly ionized, a single continuous plasma, stretching from one edge of the observable universe to the other. And so, the transformation was complete, from a universe born in plasma cooled into neutrality and reborn into plasma again. From opacity to transparency to a new kind of transparency. From darkness to scattered points of light to pervasive illumination. The journey from the Big Bang to the end of reionization took 1 billion years, 1 billion years of cooling and gathering and igniting and spreading. And at the end of that journey, the universe had become recognizable, the ancestor of the cosmos we observe today, full of galaxies and stars and light, complex and structured and alive with energy. The dark ages were over, the first stars had risen and set, and the universe finally could see itself clearly lit by the fires it had learned to kindle in the long night after creation. The light we just watched spread across the cosmos. That slow awakening of the universe from its long sleep brings us to a question that might seem strange at first. Why does any of this matter? Why should we care about events that happened 13 billion years ago in a darkness no human will ever witness, involving stars that died before our sun was born? The answer is simpler than you might think. We are made of that darkness. Every atom in your body, except for some of the hydrogen, was forged in the heart of a star. The carbon that forms the backbone of every protein, every strand of DNA, every cell wall didn't exist in the universe before the first stars burned. It was created when helium nuclei compressed by gravity in stellar cores, heated to hundreds of millions of degrees, fused together in the triple alpha process, that delicate dance of quantum mechanics we mentioned earlier. 3 helium nuclei becoming 1 carbon nucleus. It happened in the cores of population 3 stars. It's happening right now in red giants scattered across the galaxy. And it happened at some point in the past, in the star, that contributed the carbon you're breathing out with every exhale. The oxygen you just inhaled, the oxygen that's bonding with carbon in your cells right now to release energy. That oxygen came from an even hotter core, a star massive enough to fuse carbon into heavier elements. Oxygen forms when a carbon nucleus captures another helium nucleus, a process that requires temperatures above 100 million Kelvin. Only stars at least 8 times the mass of the sun can reach these temperatures. Smaller stars, like red dwarfs, never make oxygen. They live for trillions of years, burning hydrogen slowly. But they never get hot enough to create the elements that make complex chemistry possible. The calcium in your bones, the iron in your blood, the sodium and potassium that carry electrical signals through your nerves, all of it required even more extreme conditions. Iron, the endpoint of stellar fusion, forms in the cores of massive stars just before they explode. The core becomes a factory producing iron at an astounding rate in the days before collapse, building up until the star can no longer support itself. And then the collapse, the rebound, the supernova, scattering iron, and dozens of other elements into space. Some of the heavier elements in your body, the trace amounts of zinc and copper and iodine, weren't made by fusion at all. They were created in the supernova explosion itself, in the intense neutron flux of the shock wave. When a massive star explodes, neutrons flood the environment, and atomic nuclei can capture them rapidly, jumping up the periodic table in seconds. This R process, rapid neutron capture, creates elements that fusion can't make, elements heavier than iron: gold, platinum, uranium. The gold in any jewelry you might be wearing was almost certainly made in a supernova, possibly in a neutron star collision, forged in conditions of unimaginable violence and heat. Think about that for a moment. The atoms in your body are ancient, older than the Earth, older than the Sun. They'd have been on a journey spanning billions of years and trillions of miles. They formed in stars were scattered by explosions, drifted through interstellar space, collected in a cloud that collapsed to form our solar system, accreted into planets, cycled through geological processes, became part of living organisms perhaps many times, and eventually ended up as part of you. You are a temporary arrangement of stellar debris, a pattern in the cosmic recycling system, atoms borrowed from the universe and assembled into the shape of a person. And the hydrogen in your body, the 10% or so of your atoms that are hydrogen, that hydrogen is even older. It didn't form in stars. It's primordial dating, back to the first 3 minutes after the Big Bang, created in the frenzy of nucleosynthesis, when the universe was hot enough for protons and neutrons to fuse. The hydrogen in the water you drink and the organic molecules that make up your cells is nearly 14 billion years old. It predates stars. It predates galaxies. It was there in the dark ages drifting as neutral gas, waiting for gravity to gather it into the first stars. So, when we talk about the universe before stars, we're not talking about something distant and disconnected. We're talking about the origins of the matter that makes up everything we know. The story of the Dark Ages is the story of how the ingredients for life were waiting patient and invisible for the right conditions to create the furnaces that would transform them. It's the story of potential of possibility held in suspension of a universe pregnant with future complexity, even when it appeared empty and dark. There's a deeper connection too. The light from the cosmic microwave background, that ancient radiation released at recombination, is still reaching us. Right now, as you listen to these words, photons that have been traveling for 13.8 billion years are passing through the space you occupy. They're invisible to your eyes because they've been redshifted into microwaves, but they're a faint glow filling the universe, carrying information about the moment when the cosmos first became transparent. Special antennas can detect this radiation. Scientists have mapped it across the entire sky. And what it shows is a universe that was remarkably smooth, with only tiny fluctuations in temperature and density. Those fluctuations, 1 part in 100,000, are the seeds we talked about earlier. The quantum ripples stretch to cosmic size by inflation. And here's something remarkable. The largest fluctuations visible in the CMB, the biggest hot and cold spots, correspond to regions of space that are now separated by about 1 billion light years. But light travels at a fixed speed, and the universe is only 13.8 billion years old. So signals from those regions have only recently been able to reach each other for the first time. When the CMB photons were released, those regions were in causal contact, meaning they could have influenced each other. But then the expansion of space carried them apart faster than light could travel between them. Only now, billions of years later, is light from one region reaching the other. This tells us something profound. The uniformity we see in the universe, the fact that distant regions have similar properties, even though they haven't been in contact for most of cosmic history, requires an explanation. And the best explanation we have is inflation, that brief period of exponential expansion in the first fraction of a second that smooth out any irregularities and stretch quantum fluctuations into the seeds of structure. Without inflation or something like it, the universe should be far more chaotic, far less uniform. The fact that it's not is evidence that something dramatic happened at the very beginning. We stand now 13.8 billion years after the Big Bang in a universe transformed by stars. But if you could somehow turn off all the stars dim, all the galaxies eliminate every source of light except the cosmic microwave background, you'd see something surprising. The universe would still glow faintly uniformly in every direction. That glow cooled to just 2.7 degrees above absolute zero is the oldest light we can see. It's been traveling since the universe was only 380,000 years old, a baby by cosmic standards. and it carries a message written in temperature fluctuations and polarization patterns about the conditions that led to everything we see today. The Dark Ages, that 100 million year period of silence and waiting, left no direct light for us to observe. But its legacy is everywhere. The cosmic web, the filaments and voids, the distribution of galaxies, all of it grew from the structures that formed during the Dark Ages. The first stars, the population 3 giants seeded the universe with heavy elements, making later generations of stars and planets possible. And the ionization they triggered changed the thermal state of the intergalactic medium, affecting how gas behaves and how galaxies form even today. There's a misconception worth addressing. Some people imagine the early universe as a violent, chaotic place, a maelstrom of explosions and collisions. And parts of it were violent. Supernovae are violent. Stellar collisions are violent. But much of cosmic evolution happens slowly, gently through the patient accumulation of small effects over vast timescales. Gravity pulling gas together one atom at a time, clouds cooling and condensing degree by degree, ionization spreading bubble by bubble. The universe is less like a battlefield and more like a garden, growing according to rules, responding to conditions, developing complexity through process rather than chaos. Another misconception is that the universe is mostly empty, and by volume, it is. The space between stars, between galaxies, is vast and nearly void. But by mass, the universe is full. Dark matter, which we can't see directly, outweighs normal matter by a factor of 5. And normal matter, mostly hydrogen and helium, fills the space between galaxies as a thin plasma. It's tenuous, only a few atoms per cubic meter, but it's there accounting for most of the ordinary matter in the universe. The stars and galaxies we see are just the bright, dense nodes in a web of matter that extends everywhere. We've traced a journey tonight from the Big Bang to the end of ionization, from pure energy to matter, from uniformity to structure, from darkness to light. It's a journey of transformation, of organization, of complexity emerging from simplicity through the operation of physical law. And it's a journey that continues. Stars are still forming, galaxies are still merging, black holes are still accreting. The universe is not static. It's dynamic, evolving, changing on time scales both unimaginably long and surprisingly short. And you are part of that evolution, not just as an observer watching from outside, but as a participant made from the same atoms, governed by the same laws, connected through history and physics to everything that's happened since the beginning. Your existence depended on stars forming and dying, on supernovae scattering elements, on molecular clouds condensing on planets, accreting on chemistry, becoming complex enough to support life. Every step in cosmic history, from inflation to reionization, was necessary for you to be here, listening to these words, contemplating your origins. The universe before stars was dark, yes, but it wasn't empty. It was full of potential, full of hydrogen and helium waiting to fuse, full of dark matter halos waiting to collect gas, full of quantum seeds waiting to grow. The darkness was pregnant with light. The silence was pregnant with sound, and the emptiness was pregnant with everything that would come. Perhaps there's a lesson in that the most important preparations often happen out of sight. That potential can exist long before it's realized. That waiting is not the same as wasting. The universe waited 100 million years in the dark before lighting its first star. But those 100 million years weren't wasted. They were necessary. They were the foundation on which everything else was built. And now, as we drift toward the end of this story, as the last echoes of cosmic history fade into the present moment, we can appreciate the long path that led here. From quantum fluctuations smaller than atoms to galaxy clusters spanning hundreds of millions of light years, from a featureless soup of particles to a cosmos filled with structure and light, from a universe that couldn't see itself to one that has evolved conscious beings capable of looking back across billions of years and understanding where they came from. The universe looked very different before the first stars existed. But in that difference, in that darkness and silence, the stage was being set for everything we know. The actors were gathering, the props were being arranged, and when the curtain finally rose, when the first star finally ignited, the show began in earnest. A show that's still running, a show we're part of whether we realize it or not. Thank you for drifting with me through these ancient nights, through the darkness before dawn, through the silence before the first song. The story of the universe before stars is the story of patience, of potential, of transformation. It's the story of how nothing became something, how darkness became light, how simplicity became complexity. And most importantly, it's your story. The atoms in your body remember those times. They carry that history. You are a living connection to the deepest past, a bridge between the first stars and whatever comes next. The universe is still writing its story, and new chapters unfold every moment. There are still mysteries to explore, questions to answer, wonders to discover. If you'd like to continue this journey with me, to explore more quiet corners of cosmic history, more gentle revelations of science, I'll be here waiting in the stillness, ready to share what the universe whispers to those patient enough to listen. Until then, rest well. Dream of stars being born in ancient darkness. Dream of atoms remembering their origins. Dream of a universe that took billions of years to make you possible. And know that you carry that entire history inside you, written in the language of elements, spoken in the rhythm of fusion, remembered in every breath. Sleep well. Dream gently. Good night.